Hi, folks. Now we're going to look at exponential functions and how they appear on graphs and some different features of these exponential functions. And you can see right up here from my vocab list that exponential functions definitely do not look linear. They definitely do not look like a straight line. So an exponential function is going to be a nonlinear function, and it's going to take this form: y equals a times b to the x power, where a does not equal 0, b does not equal 1, and b is greater than 0. And you'll kind of see examples of these of why it's important to have these restrictions as we move through this. But obviously, if a equaled 0, this whole thing would just say y equals 0, and there wouldn't be an exponential a power part of this equation. What we're going to see with an exponential function, the thing that makes it different to a linear function, is that as x changes by a constant amount, y is going to be multiplied by a constant factor. And with linear expressions, we didn't multiply each time we moved to a new point on the graph. We added a constant value as we move to each point of the graph. And so you'll see that as we move down. We'll also talk about asymptotes, which is when a graph approaches a line but never actually touches that line. So it's a line that the graph approaches more and more closely without ever touching it. So here, the kind of invisible line that my blue graph is approaching but never touches is the x-axis here when y equals 0. And so we'll look at kind of how to look at an exponential function and determine where the asymptote is. So first, let's learn to identify exponential functions. As I said, exponential functions are when you multiply by a consistent value. But before we can check to see if the y value is being consistently multiplied by the same value, check to make sure that your x value increases consistently. So here, each time I just add 1 to the x value, and so I'm always increasing just by 1. So check that first before you look for consistency in the y value. Because if you're inconsistent with the changes in the x value, you won't see consistency in the y value, generally speaking. So now that I've looked for a pattern there, I'm going to look for a pattern in these values. And the pattern that I see here, let's see, 2 plus 2 is 4, but 2 times 2 is also 4. So let me look at the next step. It's 4 plus 2 is 6. I am adding 2 at each step along the way here. So this is an example of a linear equation. When you have a constant rate of change, you add 2 every step for every change in x. So this is linear because there's a constant rate. I add 2 with each change in x. So let's look at this other example here. Again, I'm going to check the x values before I check the y values. I'm adding 1 each time. And let's see, 4 times 2 is 8, but 4 plus 4 is also 8. So let me look at the next step. 8, that's got to be times 2 is 16, and 16 times 2 is 32. Here I'm multiplying by 2 for each change in x. Because I'm multiplying by a consistent value, this is an exponential function. So this is exponential because I'm consistently multiplying by 2. Okay, so that's what makes this an exponential function. So it's important to be able to look at a data table and identify, is this linear? Is this something else? And in this particular example, this is an exponential function. Next, let's look at this format here, y equals a times b to the x power, and how to kind of plug in values to evaluate the equations. So we have y equals -2 times 5 to the x power, but I want x to equal 3. So I'm going to plug in 3 where x was, -2 times 5 to the third power. And 5 to the third power is just 125. So if I do -2 times 125, that gives me -250. Moving on to the next example. Again, just plug in x is -2, so plug in the -2 where you see x. 3 times 0.5 to the -2 power. Now, 0.5 is the same as 1/2, so I'm going to just rewrite this as 1/2 to the -2 power. And you learned this in the last lesson. 1/2 to the -2 power, I can flip the fraction. So this will be the same as 3 times 2 over 1 squared. So I basically have 3 times 2 squared, which is the same as 3 times 4, which equals 12. And that's how you evaluate just by plugging in the given value of x wherever you see x in the equation. So let's look at the shape of these exponential functions and look at how they can kind of be transformed, how they can be changed um, by changing different parts of the equation. So far, we've been talking about equations in this format, y equals a times b to the x power. So let's look at what happens when we change that a value, when we have a multiplication factor out front. So I'm going to compare this f of x equals 4 times 2 to the x power to its parent function that doesn't have that 4 out front here. It's just 2 to the x. And I've already graphed this here um, uh, below. This is graphed in red down here. So I'll do my f function in a different color. I'll do f in green here. So my f function is really the exact same as the g function, except I end up multiplying it times 4. So instead of having, when I plug in a -2, I don't get 0.25. I get that times 4, which is 1. So I'm just taking this expression or this value and multiplying it times 4. Instead of getting 0.5, I'm going to get 4 times that much, which is 2. Instead of having 1, I get 4 times that much. 2, I get 4 times that much. Instead of getting 4, I get 4 times that much. So if I kind of plot these points on the graph here, at -2, I have a value of 1. At -1, I have a value of 2. At 1, I have a value of 4. At 0, I have a value of 4. At 1, I have a value of 8. And at 2, I have a value of 16. And so what we have here is, and I do apologize, I have a sore finger and I didn't draw the best curve ever down here at the bottom. But we have here a curve that's been stretched from the original parent function. This has created a vertical stretch. We've multiplied times 4 in the y direction. So f of x is a vertical stretch of, didn't mean to print parentheses there, g of x by a factor of 4. A vertical stretch times a factor of 4. Now, we're asked to give list certain features of this graph, f of x. It says to identify the y-intercept. Well, my y-intercept is here and let's go ahead and make a little comparison table of my f of x function versus the parent function, g of x. My f of x function, my green graph, has a y-intercept of 4. It has an asymptote of y equals 0. It has a domain. Remember, domain means all possible x values. I can use any value of x on the negative end of the set of numbers. I can use any positive x. I can go on forever. I could have x be as big of a number as I possibly want. So this is all real numbers is my domain. My range, on the other hand, it's not possible to have all numbers. If you look, my graph starts near zero, but never actually touches zero. So y can't actually be zero. Y needs to be greater than zero. And then y can get bigger and bigger and bigger on up forever. So y can go up to infinity. You don't have to write that down. You can leave it as just y is greater than zero. Usually we would write it this way, y is greater than zero. And that captures all possible y values. Y in this example cannot be negative, and so that's not part of the range. On the other hand, if we look at our original parent function, our original y-intercept was at y equals 1. The asymptote here is also at 0 as you move further to the left. Both the green curve and the red curve approach 0. Just like the green graph, we have all real numbers as our possible x values in the horizontal direction. But in the y direction, with that asymptote being at 0, our y values need to be greater than 0. So these are some of the features you can be asked about on an exponential function graph. Y-intercept, asymptotes, domain, and range. So let's do another example of graphing a function and comparing it to its parent function. This time, we're going to graph f of x equals negative 1/2 to the x power. And that negative is not, it happens after the 1/2 is raised to the x power. It's outside the parentheses. And we're going to compare this to the parent function that doesn't have the negative sign out front. G of x is 1/2 to the x power. So I've already plotted g of x on the graph. It's this black curve here, and you can I've plotted out or listed in the table various points on the graph. And because what we're doing here is multiplying our g of x function just times -1, the y values, the function values are the same in value, but opposite signs. We're just multiplying everything times -1. So instead of having a y value of 4, we've got a y value of -4. Instead of having a y value of 2, we've got a y value of -2, -1, -0.5, and -0.25. So if we plot these points on the graph, we'll have at -2, we go to -4. At -1, we're at -2. Then -1 at 0 here, 0, -1. A half and a quarter. So we are going to get closer and closer to the y equals 0 here, but never actually touch it. So this here will be my asymptote. Once again, if you compare the parent function to f of x, so this is f of x, and then I've got my parent function, which I'll write in gray, is the g of x. What are the different factors that we can be asked about? We can be asked about the y-intercept. Our y-intercept here was at -1. Our asymptote was at y equals 0. Our domain was all real numbers. Just like before, we can plug in any value we want to for x. There's no limit. So that's going to be all real numbers. And then our range, our possible values in the y direction are limited. My green graph here never gets bigger than 0. In fact, it never even reaches 0. All the y values here are less than 0 because y equals 0 is our asymptote and we never touch the asymptote. All the possible y values are less than 0. Let's fill in similarly our values for the parent function. The y-intercept happens here at y equals 1. The asymptote is again still y equals 0. The domain is all real numbers, but the ranges here are different. The range here, the possible y values are anything above the asymptote. So this is all y values that are greater than 0. So then the question is, so far every equation we've looked at has the asymptote at y equals 0, and then that asymptote kind of determines the range. We can either be above the asymptote or below the asymptote for the range. So could the asymptote be anything other than y equals 0? And the answer is yes, it can. So we're going to look at a different set, kind of different changes we can make. Up till now, all of our equations have been in the form y equals a times b to the x. But there are a couple of extra changes we could make. We could subtract a value from that x exponent, or we could add a value on to the exponential expression after we've already raised the base value to a power. So there are these two extra changes here that we haven't looked at. Maybe this is ringing some bells for you that we're using these variables h and k. These are the same variables we used when we were talking about transforming functions back when we were talking about linear functions and we were talking about vertical shifts and horizontal shifts. If you remember, when the change happened inside parentheses, kind of inside the original parent function, that indicated that the change was happening in the x direction. And then if the change was done afterwards, kind of outside parentheses, then that indicated a change in the y direction for the output values. We're going to see the same thing here. So we're going to start with the parent function of f of x equals 4 times 2 to the x power. And I've graphed that here in blue. This is actually the same graph that we drew back in part C, part A above. But we're going to do further transformations with it because we've got this subtraction by 3 up here in the exponent, and then we're adding 2. And what you'll see as we do this is you will see, hopefully, that this is a shift. This h of x function, I'm sorry, I'll write this in a different color. This h of x function is a shift of 3 to the right and 2 up. 3 to the right, because when you see the change happen inside the parentheses, even though there aren't parentheses written here, the implication is that you have, you do the x minus 3 because it's all written small. You do x minus 3 before you raise 2 to that power. That's causing that shift of 3 to the right. Remember, when the change is to the input value, the change is the opposite to what you expect. So even though there's a subtraction by 3, we're subtracting 3, it is a shift of 3 to the right. And then we add 2 after we've done everything else on the all the other parts of the calculation. We add 2 at the very end, and that's going to create a shift up, a change in the output value where we add 2 and shift the graph 2 units up. So I tried to kind of color coordinate the data points here because we're shifting 3 to the right. The output value that you see here of the original parent function corresponds to this one that's 1, 2, 3 units over. This one kind of represents the same data point as we have here. This might be easier if I label the exact points. So -2 and 1, uh, -1 and 2, 0 and 4, 1 and 8. So those are kind of the 4 points that are especially marked here in the data table. And now I'm going to draw this h of x graph where I'm going to have points at 1, 3, 2, 4, 3, 6, and 4, 10. So what you'll see here, if you continue to kind of draw points in, okay, is you would get a curve like this, which has been shifted 1, 2, 3 units to the right and 1, 2 units up. Each of those x's that I drew in blue corresponds to an x drawn in red. This x here, if I go over 1, 2, 3 units to the right and then up 2 units, that's where the new data point is. So if we draw these more complicated exponential functions, you do shift the graph. And in these examples, we do change the location of the asymptote, and therefore we change the range of the functions. So let's just do a quick table here for our h of x function. We are going to want to know the y-intercept, the asymptote, the domain, and the range. And for the h of x function, y-intercept is happening here at y equals 2.5. The domain, I'm sorry, the asymptote is at y equals 2, which is 2 higher than the original parent function because we shifted the graph 2 up. The domain is all real numbers. And the range is anything above the asymptote, so y needs to be greater than 2. Comparing this to our original parent function, our f of x, that y-intercept was here at y equals 4. The asymptote, uh, this one was back to that original asymptote is at y equals 0. The domain is all real numbers. And the range, the possible y values are anything above that asymptote anytime when y is greater than 0. So it is possible to do these more complicated transformations. Many of the equations we do will be the simpler version, but it's important for you to understand that these other transformations are possible and how to bring those other transformations about, the shifts left and right and up and down. So how do we write an exponential function to describe a situation? If I'm given a graph, how do I know what exponential function fits the graph? I know how to take an equation and draw a graph from it. I want to go the other direction now. So what I'm going to do here is if I'm given a graph, the first thing we're going to do is make a data table out of it. So when x is 0, y is 3. When x is 1, y is 12. So I'm just using the graph to fill in data points here like this. And I can tell from the graph this is not a linear equation, But before I try writing an exponential function, I should just confirm that this is in fact an exponential function. So check those x steps before you try checking y. Am I increasing by a regular consistent amount? Yes, I am. Each x value is one larger than the previous. So now I'm ready to start looking for a pattern in y values. And each y value seems to be 4 times bigger than the one before. 3 times 4 is 12. 12 times 4 is 48. 48 times 4 is 192. 192 times 4. I'm sorry, that really looks like a plus sign. So make sure that those are multiplication signs. If you're struggling to see the pattern, the easiest way to see the pattern is to take the second number and divide it by the first number. So if you don't spot what the multiplication factor is, try doing 12 divided by 3 and seeing what that equals. It equals 4. And then check the next pair of values, consecutive pair of values. I'm going to do 48 divided by 12, which is still 4. I'm going to do 192 divided by 48, and that's still 4. And it's this consistent ratio that lets me know this is, in fact, an exponential function. Now, I want to write my equation in y equals a times b to the x form. That b value is my base value. And the way you figure out your base value is you take your multiplication factor and you divide it by the change in x. So my b value here is going to be my multiplication factor, that times 4, divided by the change in x, which is just 1. It's important to do that. Most of the examples you'll see are the x value does just step up by 1, but in case it goes up by 2s or 5s or 10s, it's important to divide by the 2 or the 5 or the 10. But in this case, because we're just stepping up by adding 1 each time to the x value, we're doing 4 divided by 1. So the multiplication factor for y divided by the change in x gives you your b value. So now I know my b value. The way I figure out my a value is to use the y-intercept. So my y-intercept is here at the value of 3, so my a value is going to be 3. Now that I know my a value and my b value, I'm ready to write my equation. Y equals 3 times 4 to the x power. It's a good idea, now that you've come up with this equation, to check to make sure it works. Before you go ahead and do other calculations using the equation, check to make sure that it checks out. So if I have, I know that 3, when x is 3, y should be 192. So I'm going to test my equation by plugging in 3 where x is and making sure that I get 192. So 4 to the third power is 64. When I multiply that times 3, I do get 192. So that checks out, and it's a check to make sure that my equation is correct. Now, I've written an equation that models the scenario, but there was another part to this question. I'm supposed to find the population after 5 days. So I'm going to take this equation, y equals 3 times 4 to the x, but I know that I want my x value to be 5 because x represents the number of days. 4 to the 5th power is 1024, so I'm just going to do 3 times 1024. And when I multiply that out, I get 3072. So I know that there's going to be a population of 3072 bacteria after this population has grown for 5 days.
Let's look at one of these exponential equations and how to handle this on a graphing calculator, how to plot some data and recognize that it is exponential instead of linear. So here we have a table of data showing the temperatures of coffee X minutes after pouring a cup. So the cup of coffee starts really hot and then it kind of cools off over time. And we can see that in the data table here, that as time progresses, the temperature decreases and decreases. So we're going to use our graphing calculators to find a function that fits the data. And so let's go ahead and do this. Now, if you don't remember how to plot a scatter plot, you go to the Stat menu and you select Edit, and then you can plug in the data from the data table. Now, if there's already data here that you wish to clear, the easiest way to clear it is to go to the column heading and then click the clear button. When you click clear, it doesn't look at first like anything's cleared, but if you toggle down, you can see that the list has disappeared. Now, as it turns out, this is actually the data that we want to graph. So I'm going to go back in here and type the x values, 0, 1, 2, 3, 4, 5, 6, 7, 8. And the y values are already what they're supposed to be for this problem. And so if you go ahead and look at the graph, you can see that there are no data points here. There are a few things you're going to need to check to make sure that you're going to see the points. First of all, make sure that stat plot is turned on. We use the stat button here to enter these data points, so we need to go to stat plot, which is above the y equals button, and it's written in blue, so we're going to click the blue second button and then y equals, and that gets us to stat plot. And you can see that my plots are turned off. I need to turn the stat plots on. So I choose option 1, and I select on by clicking enter while the on button is blinking. And now it's highlighted, and so I'm good to go here. So now I can go to the graph again and see if my data plotted. I still don't see my data. But if you look at my data, my x values were quite small. They were between 0 and 10. But my y values are in the, from 75 up to 175. So I really need to kind of go up to 200 if I'm on the y-axis if I want to see my data. So I'm going to change my window settings to match the data that we plugged in. So x going from -10 to +10, that's absolutely fine. That fits the x values I plugged in. But those y values, I need those to go up to about 200. And I don't want to have a little tick mark every 1 unit. That would be kind of crazy. So I'm going to make that a tick mark every 10 units, let's say. And now from changing those settings, when I go to graphs, I should be able to see the data. Now, when we learned how to use our graphing calculator last semester, we were doing linear equations. And if I thought this was a straight line, I would fit a linear regression. But this doesn't seem to be a straight line. It seems to be a downward curve. It seems to fit the shape of exponential functions that we've learned. So when I try to fit my line of best fit, it's not going to be a straight line of best fit. It's going to be a curve of best fit. And in math, we still call it a line of best fit, even though it's not a straight line. But I'm going to calculate. So I clicked the stat button, and instead of editing the menu, I'm going to calculate this time. So I'm going to click over for the calc menu. And last time we did linear regressions, and this time we don't want to do a linear regression. We want to go down until we see exponential regression, which is option 0. So I'm going to either hit enter or just type the number 0. I'll hit enter here. And it confirms what lists we want to use. Yes, we plugged our data into list 1 and list 2. So I'm just going to hit enter, 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 enter to get through those data. So you can see here we're given an A value, we're given a B value to plug in to write our exponential equation. If you are asked for it in a question, I didn't see any questions like this in the textbook. There is a way to get this to give you R values for your regression. And to do that, you need to make sure that you have turned on, you have to go to your catalog. So I'm going to click the second button and then the 0 because catalog is written here in blue. And you scroll down till you get to the D's. And the feature that you need to turn on is diagnostics. You want the diagnostics to be turned on. So I'll click enter and I'll click enter again. And now when I go to the stat menu and choose calculation and choose option 0 for exponential regression, and then calculate. I now have R values. So if you're using a class calculator, you may need to turn that back on. I didn't see any questions that use that, but what we absolutely need to know are these, the A value and the B value, so that we can come up with the correct equation. So you can take those values and write them here in the blanks. So this is 173.95, and this is 0.900. That might be a little hard to see, but we're going to use those numbers to write our equation in the form y equals ab to the x. So let's plug in those values. I've got 173.95 times 0.900 to the x. And that is the exponential equation that we determined using technology. We haven't quite finished with this question yet, because we're supposed to use this equation to predict the temperature of the coffee 10 minutes after it was poured. So I'm going to plug in the value of 10 where my x is up here. So I'll have 173.95 times 0.900 to the 10th power. And when I plug that into my calculator, I get a value of about 60.7 degrees Fahrenheit. And so that's my prediction, that after 10 minutes, my cup of coffee will have cooled off to 60.7 degrees Fahrenheit. I hope this helps.